Welcome to The Explainer. Today, we're going to tackle a question that every analyst faces at some point. How do you actually model something that can only be a yes or a no, a pass or a fail? It seems simple, but getting it right is crucial, and thankfully, there's a really clever solution.
Okay, so here's what we've got on tap. We're going to start by really nailing down what this yes or no problem looks like. Then we'll look at the simplest way to handle it, a straight line, and see why it's got a pretty fatal flaw. After that, we'll bring in the hero, the S-curve solution. We'll put the models head to head, and then we'll wrap up with a little challenge for you. All right, first things first. What kind of questions are we even talking about here? We're diving into situations where the outcome isn't some number that can be anything. It's just one of two things, a simple binary choice. So many of the biggest questions in life, and definitely in business, really just boil down to this. Is a mortgage application getting approved or denied? Is a customer going to stay or are they going to churn? It's these kinds of black and white outcomes we want to get a handle on and hopefully predict. So, in stat speak, we call these binary dependent variables. We basically take the messy real world and simplify it into two buckets that we label 0 and 1. So, for the mortgage data we'll be using, a denial is a 1 and an approval is a 0. The whole game then is to build a model that can tell us the probability that we're going to see a 1. So where do you even start with this? Well, the most natural place to begin is with a tool that probably feels pretty familiar to a lot of us from basic stats, just drawing a straight line through all the data points. And this has a name, of course. It's called the linear probability model, or just LPM. You're literally just doing a plain old linear regression. But because your outcome is only ever a 0 or a 1, the prediction that the line spits out is treated as a probability. It's the chance that your outcome is a 1. Now, you can probably guess the big appeal of the LPM. It is so simple to understand. That coefficient gives you a direct answer. In our mortgage data, for example, the coefficient for the payment to income ratio is 0.60. That means that for every 10-point jump in that ratio, the model says there's a 6% higher chance of being denied. Super straightforward, right? And yeah, that's the whole appeal, right? It's super easy to run in any software, and the results are a breeze to explain. No complex math, no weird functions. But, and this is a big but, that beautiful simplicity, it comes at a very, very high price. And this is where things start to go off the rails. That simple, beautiful straight line, it runs smack into a huge logical problem that kind of breaks everything. I mean, just think about it. Probabilities have really strict rules, right? They can't be negative, and they can't be over 100%. A probability of, say, 110% is complete nonsense. But a straight line, well, a straight line doesn't know that. It'll just keep on going, up or down, forever. And this graph just lays the problem bare. It's perfect. All our actual data points are either down at 0 for approved or up at 1 for denied. But look at that blue line, our LPM. Way over on the right, it's predicting probabilities greater than 1. And on the left, it's predicting probabilities less than 0. These aren't just wrong, they're literally impossible. So look, it really comes down to this. The LPM has two huge deal-breaking problems. First, as we just saw, it can predict things that make no logical sense. And second, on a more technical level, it messes up a key assumption for regression, a problem with a fancy name, heteroscedasticity. The short version, it's just the wrong tool for this kind of job. Okay, so a straight line is out. We need a different shape. And that brings us to the real pros, the two industry standard solutions for modeling these yes or no outcomes. What we're looking for is a model that's basically hardwired to respect the rules of probability. We need a curve that's guaranteed by its very math to live between 0 and 1, so it can never give us a crazy answer like 110%. And that's where two heroes enter the story, the Probit and Logit models. Now, don't let the names intimidate you. The math behind them is a bit much, but the core idea is actually really simple. Instead of forcing a straight line onto the data, they both use this elegant S-shaped curve that's always squeezed between 0 and 1. And just look at this curve. This is the elegant solution right here. See how when the payment to income ratio gets really high, the curve just flattens out and gets closer and closer to 1, but it never touches or crosses it? And it does the same thing down at the bottom near 0. It perfectly follows the rules. Okay, so there is one little catch with this lovely S-curve. The effect of any given variable isn't constant anymore. For people who are kind of on the fence, right in the middle of the curve, a small change in their income ratio has a big impact on their probability. But for the people at the ends, the surefire approvals or denials, that same change barely moves the needle. It's more realistic, but it does mean we can't just read the coefficient and get a simple answer anymore. All right, so we've got our three contenders, the simple but flawed LPM, and our two sophisticated S-curves, Probit and Logit. So how do they really compare when you use them on real data? And here's something that might surprise you. Even though the math under the hood is totally different for Probit and Logit, in practice, they usually give you almost the exact same answer. The choice between them often just comes down to what's common in your particular field. Don't believe me? Take a look at this. We've laid the Probit and Logit curves for our mortgage data right on top of each other. You can see the black line and the blue line are, well, they're practically the same line. They are incredibly close. And this table just confirms what we saw in the graph. We're looking at the predicted difference in denial probability between a black and a white applicant here. Look at Probit and Logit, 15.8% and 14.8%. Super close. But the LPM, it's a bit of an outlier at 17.7%. It just goes to show how using that flawed model can actually change your conclusions. So what's the bottom line here? It's pretty clear. When you're dealing with a yes or no question, you gotta use the right tool for the job. The LPM is simple, sure, but it's fundamentally broken for this purpose. Probit and Logit are the correct, reliable choices. And while you do have to be a little more careful when you interpret their results, you can trust that they're giving you answers that actually make sense. Okay, we've covered a lot of ground. So now it's your turn to put this into practice. We've got a final question for you, this time using a totally different data set. That's about what predicts whether or not someone gets a college degree. All right, on the screen, you've got some results from a Probit model. Your mission, should you choose to accept it, is to use these numbers to calculate the probability that a student living 5 miles from campus gets a degree. We've even given you a hint to get started. This is exactly how you go from theory to real-world application. And it really makes you think, what other yes or no questions in your own work, or even just in your life, could you tackle with a model like this?